Also, X is a metric space. And so we say that the slope dimension of X is at most n, and only for every number that exists, would be a uniformly bounded covering of X, say UI, and I said that again, this will be covering is more interesting. Okay. First of all, what is a covering? So a unit is a covering interface. Effectively, the union, first of all, this is a set of subsets of X, and we'll say that this is a covering if the union of all elements of the set is actually equal to the whole space X. Next, what is uniform? What is uniformly bounded covering? So uniformly bounded covered U is covering so that every for every element. The covering, the diameter is at most big. And last, what is that implicitly? So then the implicitly covered is the mean number. Is the mean number n. It's at number exists. If it doesn't exist, then we will use this infinite. So is the mean number n so that for every smart ball. Okay, smart ball is a ball of taking part for every ball effects. So that every one represent in the set of many elements for the cover. Right. So one important thing is that dimension is quasi-geometric dividing. And this property actually helps define the dimension for finite Z. So given it's a finite Z group, and along with the finite Z group, we find the dimension of the again after the dimension of the daily this Tselekidis set is whatever. We go to the dimension in process to divide, and this is the well defined. So from the definition, it's obvious to say that if you have expand such properties, then there's no dimension of expand with the infinite. It's smaller than the dimension of X. It's something similar. Well, something like that also happens for the field. So you have a finite related group of Z. Then there's no dimension of X is more than the dimension of Z. That is not obviously it's part of it. It's a little bit, but it is very normal. So why dimension is important? Important for the theory. But you can we know that the dimension is passive divided. It's divided, and it helps to classify groups up to isomorphy. And second, we know that groups we find interdimension satisfy do not go. Third more flow. Any questions so far? Okay, so let's see a few examples of how to how to compute some dimension. Okay, so maybe there is an example is that of finite group. So let's say if it's a finite group, then we want to consider some dimension of the finite group. We consider another, and we want to construct this UR covering. And for that, the UR covering will be actually another thing. And it's going to be clear that the dimension of the finite group is actually zero. Right. So what about now? What about the native cycle? What about the native cycle? So we know that the Z is actually the scale of Z is actually corresponding to the real line, and so the real line. You want for every R, D for every R, you decompose the real line like that. So for the part, then we consider for every ball, any ball I intersects the covering to one element here or at most two. So so we consider the dimension of it is actually one by one, but also something that I don't mention, is that when we have a connected metric space, then the dimension is at least one. So we have one. Maybe a bit, another example is what about the two? Again, the two is actually related to two. We have the plane here. And again, we want for every R, we decompose the plane like that. And again, we consider for every polar, and a polar intersects power and power in one set, in an element, or two, and you can find more than four, more than three. So we consider the dimension of that which are most, more generally, we have what the dimension of the plane is that most is actually exactly. Maybe something harder is what about the dimension of hyperbolic. So, and right. So again, we start with so we have a group it's controlling. Finally, the second the group, and we have the daily graph. The group with respect to this the set is that there is a okay, so we want to find the covering of the daily graph. Is bound by the distribution. How we do that? If you can't have we can consider that R is really done in delta. It's not can do that. Here we start with the ball of values 20 times R, and you consider and around this board. So what the board of the design will be the first element in the pattern, so it will be and so the idea now is to so the decompose is to find line. So we'll find the pattern for the is of the any line, say U and R, and so and they want is covering the gap from the union of all those. Covering are not the previous let's see how we can do that. So we have this again. We have the ball of radius 25 plus n times 10 minus radius 20 plus n times 20. Okay, and we want to find the covering of this modularity. Okay, so for every element, now this is actually the sphere of this sphere of the formula. Now, for every element in the sphere, for every element x in the sphere, I define so we define let's say x is actually u and x is actually all the elements y in the design line. Such that the relation gamma from the identity from into the element y here. So that this intersects so this and that. So this will be our set U and the union of all those and we find and the union of all those given. So the connection of all those sets the covering of this design value. And now you don't have to say that you don't have to say that the diameter every set is actually bounded by. So the thickness of the line is actually enough. So we have so it's immediately bounded. And not the first time to find the issue. Let's bound with the so we assume that there exists a 12 element of the covering on given x now from given x2 so that the distance of those elements is bound to my well. So if this happens without consider, we can detect the x1 and x3 because this is u and x1 and this is u and x2. And so what we know is that the distance is smaller than y. So that this element y1 and y2 will be smaller than y. Okay, so we consider that the density is there, and because it is the Kelly is hyperbolic and R is bigger, much bigger than delta, you can see that the distance between those epsilon and h6 is compared to the delta. By this argument, you can show that the average electricity of those patterns is nothing bound by the kind of the bone or detail like that with red data with respect to the electronic set as yes, we have we bound the heat to those how we yeah. What we have done is the following so we organize that. But still we haven't bound the piece of the whole of the whole it's now it's important to observe the following that any algorithm intersects either one element of the cavity, either one so that either one and line or at most two. So that in the case of the whole cavity would be actually for the piece of the whole cavity will be actually done by two times. Yeah, the cardinality of the whole and so that's because the bound doesn't depend on depends only on the delta s. We have the dimension from n to 2 of let's see, defined by this times that nine of the ball and so on. Right. So any question for this? But so what we know so far about the measure what is known as I mentioned, finance dimension, actually we know something in general that is known. So we know that intervention of related is able to close finite, assuming that the variability is also and this was a term of C, this term of C, and it was put in 2005. So what we know is another example is about the market rules. So we know that the dimensions of market rules is 2. And this is mine. Which group of one rules? One related.
This one is kind of related.
One relator.
Yeah. Yeah, I mean, the group is has a presentation. Yes, this is just a finite set, and there's only one here. Naturally, I put some more. So actually, I can follow. So I put that if we have a one group, then one of the following is true. So either C is actually a finite cycle, and then the second dimension is 0. Or the second case is Z is actually 3. Or 3 free product is the finite cycle group. Yeah, I consider the finite cycle group. And then the second dimension is exactly 1. And the last case is that when Z is either free in the convertible or not infinite cycle or free in the convertible fit products with a fit group. And in this case, we have the fundamental exact. Right. And this is actually one of the rare cases that we know exactly the dimension of class of groups. In general, we know that some groups have finite dimension, but we don't have good enough bounds. And actually, there are cases that we know that a group has a class of groups have finite dimension, but we don't know nothing about any other bound.
If a group has a classifying space of dimension D, does this imply that it has asymptotic dimension at most D?
I'm not sure, yeah.
If it has what?
A classifying space. Self-complex only uses up to D cells.
Yeah, I'm sure. Probably, yeah.
Could you explain? You mentioned that there are some classes of groups.
Yeah.
No other dimension is finite, but don't.
Yeah. So the class group called atom group, and there's a subclass of atom groups called XLRs. So XLR atom groups is atom groups defined actually by graph, by labeled graph, and actually are labeled by natural numbers. And XLR atom groups are actually atom groups that every label is at least. So we know that this have finite dimension, proven by Sisto and some other research. So we proven by Sisto in 2000 years, right? And some other mathematician. And actually, this class of groups is hierarchical. But so we know that this could have finite dimension, but we have nothing about any of the bound. Right, so I think the idea was to embed these starting groups into a product of finite range hyperbolic graphs. This hyperbolic graphs has finite dimension because the uniform look at finite, but we actually but actually we don't know what is the dimension of the graph. Is there anything you know that are finite dimension? Right. So some examples are one of them is a subclass called those groups are groups that every label is true. We know the name of those. Right, so what is this example that the line graph? So the small gamma is after the maximum marginality of so I think it's the graph that every vertex is connected. And so there are two groups. The ones mathematician neat line. In 2010. And I have also a different group in 2019. So it is another idea that we know the data dimension of the class. But yeah. Yeah. So another example is the vector group. Okay, and you know that finite dimension. And after the effect of the are going to be important. So the book is found by the same number of me, and I put it in 2020. Right. But yeah, it's sometimes not much, sometimes no. Right. So we don't know exactly what this is supposed to do, but we have a nice about. Right. So another class is the another class is Martin class group. So Martin class group. finite. We don't know the dimension of the group, but we know it's finite, and we could not define it in 2010. Between them. And after the more after, which after the stage of the dimension of highlight the word is not finite. I think it's probably not many. And I see them. And
For which groups?
highlight the word groups. Highlight the word.
What?
Highlight the word.
There is this recent important generalization of hyperbolic groups.
Yeah. And actually, mathematical.
What is the word hierarchy?
And actually, mathematical is not highlighted. So this is. But actually, it was five things. Right. Then after some other now. And maybe last time. Example groups. And we want to know what is the fundament of the fundamental group of this example groups. So the best known number of the result of one is the information of the fundamental group of this the group is bounded by the maximum of the assumed dimension of the various groups, comma the assumed dimension of these groups. And this is a term in 2020. So now let's see a few techniques. Sorry. Right. So getting here the following. So we know that one of the group has bounded with dimension by 2. So can we generalize that to maybe two-related group? And the answer is no. So there is a two-related group with infinite dimension, and this is the quantity of infinite dimension. And another group with also infinite dimension is actually the negative quantity. So there are groups with
Mainly solvable groups. Take leap for the Z with Z.
Yeah.
Or they contain Z to the infinity.
Okay, yes. An important group as right. Yeah, an important group of time. Right, and so now let's see the techniques of how to prove an answer to bound. Yeah, not yeah, sometimes not nice, but yeah. So I think it's how to put other bounds for the dimension. The first one is so I think that is a group, a financial group, which is defined measurement property. So in this case, the most popular technique is actually try to decompose the space, the telegram into annuli, and then give the geometric property. find another bound in this view of so this I think has been used for category, for example. So still the thing so now the second thing that we have in blue this is defined by representation. So in this case, I think the first thing you have to do is try to see the group as a graph of groups. Actually, not as a result as a result of the and then use my theorem. Use the theorem about the dimension of parameter groups. So I use the technique for running the group. For running the group, I also use it for the groups. And I have also used for some other groups. Yeah, I have used random groups and some other. Another thing you can do is really so helpful, and you want to find try to find a suite of groups such that you can relate in there. And by suite of mean I mean that the financial dimension. And I have used this technique for one day. And maybe the last one. So is try to find a metric space. Metric space. Very suitable. That the acts in the space nicely, and by nicely means the dimension is can bound by the dimension space. And this the link have been used for map of objective. And so the last section is some of the problems. Problems. Yes, first we need do what we do. Finite. So in general, we don't know whether finite is finite. We know some that, but generally we don't know. Well, in general, there are many problems. So, for example, we don't know whether the what problem solved or whether they are or whether they are cause free. And I have conjectures about that. the conjecture that the dimension of finitely group is bounded by the simple plane. And I have my conjecture when the simple plane is not when it's not most of the cases. Not come up in this bottom. And another thing I have is that so I have put like that if my conjecture is true for Artin groups defined by complete graphs, then for any Artin group. Okay. I guess another problem is about the zero groups. So zero group. Well, in general, we don't know, but there's a theory that that's zero group. Yeah, yeah. Okay, so the only thing that we know about those that when we have a group which acts on finite dimension, that's the complex. Then if that that's nice on finite dimension, that's the complex. We know that as finite dimension. In general, we don't know. So I would expect that this is false. So another thing sort of problem is about the dimension of them. So we don't know whether it's finite. So then we know it's about the A1 and S2, but that we know not for the groups, the combination of groups. So I have two more questions. So one question is do dimension because the cognitive dimension for question free groups such that when both are finite. So there are not equal, but when both are finite, we don't have incardism. But Christina suggests that marking class groups could be a combination. And the last of the problem that I will mention is quite very simple. That's the problem. So as soon as you have a finite group, you see that the 3 times z is equal to 3 times z this information C. That's one. Yeah, so what is true is this is true when the dimension is true when the dimension of C is at most and is for the volume. By the way, there are examples of graphs. So there are examples of graphs. There are graphs. Y such that the dimension of Y and the number is not the dimension Y. So and yeah.
So, but the conjecture is that the product is.
Yeah, there's no dimension of the product is dimension of group. Yeah, that's one.
So you don't have such conjecture for arbitrary pair of groups.
So
You don't have such a conjecture for an arbitrary pair of groups.
You see there are graphs Y, but are there groups H such the dimension of G cross H?
Yeah, there's also yeah, let's talk about it.
Thank you very much. Other questions by the audience?
You mentioned that if we go to implicit needs, that's because it's measurable with.
So the way that you know that both group contains, for example, the product of this. If you go to this and so Actually, you have something like, you have something class related to actually inside. And this actually is true for any event. So we have something like that for any event. So it's very bound.
Are there any examples of motion groups that have finite?
Right, so this,
Also, or
right, so we don't know, so we don't know, there's financial.
And there are no groups of intermediate growth, right? In all known constructions, I believe, right? There are, right, including very recent one like Valodi's examples. All groups of intermediate growth would have a copy of Z plus infinity mathematically inside, right?
Yeah.
There are no, I think, no candidate at all.
No. The only way we can prove exponential growth, the only way we can prove intermediate growth is precisely by having this self-similarity. Hopeless to adapt the methods away from that.
So we don't know at all.
Yeah.
It might be true, but seems to be a very difficult problem, right? In the spirit of other problem.
Yes, well, there's just one group of intermediate growth, really. There's just one group of intermediate growth and many variants. But they're all really very close cousins.
But I think it's a very intriguing question to maybe to prove. So you have a group of intermediate growth. How we maybe can prove that it's always has infinite dimension.
Yes. I would try to think more about the free Burnside groups. Quite possibly something can be said on them. They look close enough to hyperbolic groups.
It's not known, but it's reasonable to ask indeed, what is the symptotic dimension of Burnside? It might be fine, maybe, but
It might be one.
no, not the one.
No,
Not many. It's at least two.
Right, so
I was wondering.
I have the group with the but
But Burnside groups are not finally represented, so.
yeah.
I have a question about your first result that you mentioned about one related groups.
Yeah.
I believe many questions about geometry of one related groups is subtle, right? So and I believe some well-known questions are still open. Is it right that we still don't know how to characterize hyperbolic one related groups?
Well, one thing that we know that if Papadopoulos or the group is hyperbolic, but we cannot. There's not characterization of one related hyperbolic groups in general.
But there is no conjecture, right? Something like either you have bounds like solid, not
right.
There's a subgroup, or you are hyperbolic, right?
Yeah.
So, and I believe it's still very much open, right?
Yeah, it's open. Yeah, right.
And in your picture, when you computed and you proved the symptotic dimension is 2, but I wonder if there is something, it's always 2, but unless it's 1, but is there something that can distinguish two cases, hyperbolic and not hyperbolic?
No, I didn't.
But on the level of covering, so the dimension is the same, non-trivial cases which will be 2, but no way somehow to distinguish on the level.
I didn't for any.
In the proof, you don't see it.
No.
In some sense, it's also related to understanding hyperbolicity of H&N extensions, right? Because when we tell groups are H&N extensions, that's the whole point, that they're an iterated sequence of H&N extensions. And I think that's also open. Really understanding which extensions.
Is it true that an H&N extension of finitely? So is it true that if you take an H&N extension of a group with a finite asymptotic dimension, you get a group with a finite?
That's graph of groups, yes. That's his graph of groups.
Yeah, it is right. So so the corollary from my theorem. So we have some dimension of it's a different zero then the dimension is found by the maximum of the asymptotic dimension Z on the full dimension of n plus one. So for example, if n has a full dimension smaller than Z, then this has this is a dimension Z. So when so if the dimension of the sum of n is smaller than the dimension of Z, then the dimension of this as an extension is actually the dimension of Z. So yeah, no.
I have a sort of vague and general question, which is I heard many talks about this asymptotic dimension. And isn't there something like an asymptotic cohomology in the spirit of, you take the check cohomology of covers, and then you also construct something which is asymptotic. Right, that would be a whole set of vector spaces instead of just a number.
Right. So first, I defined this was deterministic, and right. So he wants something like the cohomological dimension here. Right. But another kind of definition of cohomological dimension. And I think he proves that for some cases, this asymptotic cohomological dimension is equal to asymptotic dimension. But yeah, there is.
So there is an asymptotic cohomology?
Yeah.
More questions, remarks? No. Thank you very much. And we meet again at 4:15.
4:15, there is a tea break. There are some biscuits and some